ring theory. So today we are going to start some new structures of rings and going to see the properties of these types of rings. And let me start with some ring structure. Let you have a set, you have a non-empty set, right? Let so just let me set up the situation. Yeah, okay. Yeah, so what you have is, initially suppose that let what is happening, let x be any non-empty set. Okay, you have a set which is non-empty, and r plus dot be a ring, right? You have these two things, and define, you have to you will define rx. What is that? This is actually, I'm defining in such a way that all those functions such that if x to r, right? So this is a structure, this is going to be a set, and I'm going to define the algebraic structure in such a way that suppose the addition, suppose I am going to write this as a ring structure, so I have to define two operation, right? So first you will define the plus operation as, if you have two function f comma g is inside rx, so there is the function of f x to x, there is no continuity is needed, nothing is needed, just as a function x to r, right? So suppose if f comma g are two functions in rx, so I will define the the addition f plus g at any point x is actually fx plus gx sorry, for all x inside x, and you will define the multiplication in such a way, so f comma g is two function in rx, and you will define f dot g at x as usual multiplication fx dot gx, right, for all x inside x. Okay, so you have to show this rx, which rx with this plus and dot is going to be a ring. You have to check for the properties, check. Okay, this is going to be a ring. So what is the additive identity here? So this is the zero function. Additive identity is zero constant function. Okay, this will be the additive identity here, right? So let me take a particular example for that. So let me take this example. Suppose your ring is r and the set x is 0 comma 1. What is that? This will be all those function f's, so that f 0 1 to r means the real number r. Okay, so suppose this is the this is our ring. Okay, now I'm asking one question. I'm defining the function fx here. Fx is 0, sorry, you take here 1, this is 1 whenever 0 less than or equals to x is less than or equals to half. Okay, and 0 whenever half is less than or equals to x is less than or equals to 1. So I'm asking this question, is a 0 divisor in R01? Is it a 0 divisor or not? You have to check what the, So for zero divisor, you have say clearly this is a non-zero function, right? So you have to find a non-zero function g such that the f dot g is 0, right? So for that, if it is a zero divisor, so for that for that there exists a g which is non-zero inside R01 such that f dot g at point x, this is going to be 0 for all x inside 0 comma 1, right? So can you take one function like g of x, you arrange in such a way that whenever this is 1, you take this to be 0 in the same domain, 0 less than equals to x less than equals to half, and whenever this is in 0, you take any non-zero number, suppose take 1 whenever half is less than equals to x is less than equals to 1. So you can feel that f dot g at x is 0, where g is a non-zero function, so this is going to be a zero divisor, right? This is a zero divisor. Similarly, this is also a zero divisor, right? So this is a zero divisor, right? So can you think of units of this function? Can you think of units in R01? What is R01? R01 actually basically f to R functions. So what are the units? Suppose f is an unit. So for unit, so let f be any function, f be an arbitrary function, this 0 comma 1, right? So for unit, what you should get, what you should first you should get the unit. For unit, you need the unity, right? This, what is the unity? Suppose first question, the units not unity, suppose what are the units in this ring? So for unit, what you need for the that unit mean the multiplicative identity, that's it na. So for let f be inside f, so f dot g at x you should get fx, right? You should land into fx for x inside 0 1, right? So this is I am looking for a unity, not unit right now. Later on we'll focus on unit. So suppose if for a unit, you need unity, right? Unit means 1, unity. So this implies that fx gx, this is equals to fx, right? What does it mean? We take this implies that gx to be 1 for all x inside 0, you take gx to be 1, this will work very nicely for this. For any f, you just take this constant function 1, the unity element will be that. So unity element is constant function 1, right? Gx equals to 1 is unity, right? So can every suppose, see, for every ring, this kind of rings, can we find unity always? My question is, for any ring, for any this kind of ring, so can we find unity? So for example, we take 2z 0 comma 1. What does it mean? This is defined as f function f such that f 0 1 to 2z. You cannot find any unity here. There is no unit because 1 is not inside 2z, right? Because you have to choose, you have chosen here gx to be 1, right? So if your ring has unity, that this ring, your ring is here, right? This is your ring. Your ring has unity, then you will have unity. If your ring does not have any unity, suppose r is r, there is 1, this ring has unity, this ring has unity, then you are only able to find the unity. Okay, otherwise if you don't have, suppose this, you cannot have this, because you have to choose gx, and gx should land into 2z, right? But for 2z there is no 1 at all, so you cannot choose gx to be 1, because it should land into here. So this is not, it is not possible at all, right? So if you need unity, then your ring should have the unity. Ring means the main ring. This is a set. We are starting with the x as a non-empty set and as a ring. If your ring has unity, this implies that the r to the r01 has, sorry, rx has unity, otherwise you cannot say. So I'm going to prove this statement right now. So let me just, yeah, what it says, okay, this should before proving this, I want to discuss one more thing here. So yeah, I told for the units, right? Here I have told about unity. Now can you think about units? Now I am going to back to question. Can you think for units of r01? So for units, what is the definition of a unit? Just go with the definition. U of r01. What is that? All those functions f inside this r01, r means the real number, right? So f dot g should be 1. 1r means the constant function 1, right? So it means that all those function f inside the r, okay, this is just a second, for some function g, okay, for some g inside r01, you should get 1, right? So if 01 such that fx gx should be 1 for some g inside here, right? So this implies that you should get fx gx should be 1, right? So what are the choices for g here? So if you have to choose gx to be, from here you have to choose gx to be 1 by fx, but 1 by fx is defined only if x is not inside, fx is not 0, fx is not 0. This is only defined only if fx is non-zero. This means that x is not inside range of f, sorry, 0 is not inside range of f. Are you getting my point? Just let me clear one more time. So you have to choose f x dot gx, you should get it 1. For the unit you have to choose g, right? So in terms of gx, what you will get? 1 by fx, but 1 by fx is defined only if your fx is non-zero, for x inside 0 1, right? 0 1, okay. So fx should not be 0. What does it mean? It means that x should not be inside the range of f, right? Are you getting my point? If, sorry, x not x, 0 is not inside the range of f. If 0 is inside range of f, then 1 by fx will not, you cannot define here. That's my point, right? If 0 will be, fx is 0, suppose fx is 0, So 1 by 0 will not define. You cannot define 1 by 0, right? So this cannot be inside the 0 should not be inside the range of f, right? So this is my point here. Am I clear? I think I am clear with you. So I am assuming all the functions here. So 0 should not be in the range of f. If 0 is in range of f, then there will be problem. So if inside, what are the units in 0 comma 1 such that 0 is not inside range of f. In all other cases you can define. If there is non-zero, then obviously you can find 1 by gx, sorry 1 by fx, right? For f you can get 1 by fx. That okay. So that's it, range of f. That's it. These are the units, right? These are the units. So these are the units for the ring R0, R to the power 0 1. That means the set of all functions from 0 1 to R, right? So there is a, I have in the last class I have proved that if it is 0, if it is unit, either so if it is unit, it cannot be a 0 divisor, right? So let f is a function, or f is a function on R01, right, with 0 is inside range of f. I want to see whether if 0 is inside range of f, will it be a 0 divisor or not, and f should not be not identically 0. Okay, so if 0 is inside range of f, what will happen? I just wanted to see that. Suppose if 0 is not inside f, this will be unit. So what do you expect? If it is not an unit, that means it must be 0 divisor, I guess. So suppose 0 is inside range of f. Okay, f is a function. Suppose 0 is inside range of f. Will f it be a 0 divisor? Suppose f is, so f is non-identical 0 and 0 inside range of f. That means there exists x inside 0 comma 1 in the domain such that fx is equals to 0. At least for 1 0 there will be 0 inside range of f, and f is not identically 0. So define g of x 0 1 if x inside zeros of f, x inside, sorry, x not inside, x inside zeros of f. What is the zeros of f? Zeros of f means the points at which f is 0. Okay, zeros of f means what do we mean by zeros of f? That means all those points inside 0 comma 1 such that fx at which fx is 0. This is zeros of f. So if this is your g, if x is not inside zeros of f 0, and if x inside zeros of f, then it will 1. Then you can feel f dot g at x equals to fx gx. This is 0 for all x inside 0 1, right? So this means that if 0 inside range of f, this implies that f is a 0 divisor. Okay, if f is not a 0 divisor, sorry, if is not a unit, that means that 0 does not inside the range of f. If this is 0 inside the range of f, this implies that f is a 0 divisor. Okay, oh sorry, it's extremely okay. So now I am going to prove some theorems or some propositions here, I guess. Now example is over. Now I am going to write some theory. And so let me write formally Rx. What is this? All those function f such that f x to r. Here R is a ring, right? Functions actually. X is non-empty, R is ring, right? So I am going to prove that Rx is commutative if and only if R is commutative. Okay, so proof. Okay, suppose Rx is commutative. Rx is commutative, right? Suppose I'm writing in short, right? So Rx is, suppose Rx is commutative. So let f comma g inside Rx, let, right? So what is that? That means if Rx is commutative, then you can write f dot g equals to g dot f. This implies that f dot g at point x, this is equals to g dot f at point x. At every point they should have same value. That means that fx gx, this is gx fx. See here, fx is a member, f is a function from x to r. What will be fx? Fx will be inside r na. So fx gx is inside r, gx is inside r, this is inside r, this is inside r. So if this is commutative, then this has to be commutative na. R is commutative because fx, what is fx? Fx is nothing but a element in R, right? If this is commutative, then this should have to be commutative. There is no other choice. Commutative. Is it clear? Because this is an element in R, this is an element in R, this is an element in R, this is an element in R. Okay, so R has to be commutative. There is no other choice. Proof is very easy. Now you consider the reverse part. How will you consider the reverse? Suppose R is commutative. I guess the similar proof works here. Just suppose R is commutative. So anyways, so let R is commutative, right? That means, and let f comma g, two arbitrary function in Rx. Okay, so what will be f dot g at x? This is actually fx gx, this is inside R, this is inside R. So R is commutative, so you can write it as gx fx. This is actually g dot f at x. Okay, are you done? F dot g equals to g dot f. This implies that Rx is commutative, right? Proof is over, right? So similarly, you can prove that if Rx is a ring with unity, then R is a ring with unity. If and only if condition on this also. Rx is a ring with unity. If and only if R is ring unity. Proof. Similar proof works here. I guess this should be easier. Suppose you consider for the easiest first. Suppose the reverse first. Suppose R is a ring with unity. Suppose R is a ring with unity. Okay, RU, ring with unity. Say unity element is 1R. Suppose. Okay. So how can you proceed for that? So fx R is a ring with unity, suppose 1R, right? So you take fx, R is a ring with unity. You have to show this Rx is a ring with unity. Suppose fx is 1 for all x inside x, and f x to R is a function. Okay, fx equals to 1. Then for any g, g inside Rx, g dot f at x, this is equals to gx fx. This is actually gx, because fx is 1, right? So this implies that fx equals to 1 f, see here, 1r. Okay, this is 1r. Suppose x is a function, you have defined fx to be 1r here, 1r, you can take it to be 1f. There is no issue. See, f is a function from x to r. So r has 1. So I am defining a function fx such that if x is equals to 1. This one, nothing but this one. 1r, or you can take 1f. There is no issue. This one I am going to write this one. This one is here. Right? So for this one will be an unit, because f is a function from x to r. I can define for every x, I can define this to be 1 at 1. So this 1 or fx, this is going to be 1. This implies gx fx equals to 1. This is unity. So fx, this is equals to 1. You can write it 1 at f is a unit of unity. Don't confuse with unit and unity, right? Unity is the the multiplicative identity, and unit is for every element. Unit means for any element is said to be unit if there exists some element such that a dot b is the unity element. A dot b should be the multiplicative identity, right? So this is unity element. So the first part is done, one part. Now we just reverse part. How do you proceed for that? Reverse part is done, forward part is left out. So you have to show what you have to show. Suppose Rx is a ring with unity, you have to show R is a ring with unity. Suppose Rx is a ring with unity. Suppose Rx with ring with unity. Ru means ring with unity, right? Say f is a function which is the unity of this function. Okay, unity of this ring structure. So if f is in unit, so you must have this property g dot f at x. This is actually gx dot fx, right? This is actually gx, because f is a unit, right, for every x inside x, right? So this is an element of R. This is an element of R, right? So fx is a unity of R. But why? See, this element is lying inside R. This element is landing into R. Okay, but why this should be a unit? Fx is a unit. Why? So for that, what you can do, I am going to give a concrete argument here. So suppose g dot f, this is equals to x, gx fx, this is equals to g, because f is a unit, right? So this element is a member of R. So why this is true? This is also in R. This is also in R. So this fx must be an unit, right? Fx must be an unit, right? So whatever the element will be, this is going to be an unit. Why this is an unit? Let R be any element in R. Define the constant function h x to R defined at h of x, this is actually R, for every x. So h is clearly h is inside Rx, because h is a function from x to R, h is inside Rx. The Rx has a unity, f, because f is a unity here, f is a unity, Rx has a unity f. So if it has unity, so you can write, so h dot f, this is equals to h, right? This implies that what is h? H of x, f of x, h of x, what is h of x? H of x is R, f of x, this is equals to R, right? This implies that this element is going to be unity of R, right? This is going to be unity of R, right? Am I clear? So this part is also done, right? So this, and if and only if statement, if Rx is a ring with unity, then R has to be ring with unity, and if R is ring with unity, then Rx has to be ring with unity. There is no other choice except this two. So now I'm going to write, suppose what you have is, suppose you have a ring R1 such that, which is R defined as R01, what is that? This is all those function f from 01 to R. Suppose R2 you have C01, C01 comma R, this is real number R, okay? This is defined as f 01 to R, this is real number R, continuous, okay? This is important. So I'm going to give a question here. Does there exist a function f R to R which is continuous such that fx is equals to 0 at exactly one point Yeah, you can of course give, this is very easy. Yes, what is that? You choose fx to be some x minus alpha, okay? So this is vanishing only at alpha, exactly one point, this is fx is 0 at alpha, right? So I am going to start question number 1. Question number 2, does there exist a function f such that R to R which is continuous such that fx is non-zero at exactly one point The answer, you just verify there does not exist any such function which is continuous at 2R such that fx is non-zero at exactly one point. The rest all the point is 0. You cannot choose this kind of function. You cannot have. So this is answer is no. You cannot find. Why? You should think in yourself. So does there exist a function f R2 are continuous such that fx is non-zero at exactly one point? You cannot choose such a function. You cannot find such a function, right? Okay, fine. You can also observe that C01 R is a subring of R01. Why? These are the specific functions which are continuous from 0 to r, and these are all the function. So this is already contained in here, right? First of all, this is a subset of this kind of functions are already contained inside this. These are just function, these are continuous functions, right? So there is continuity is added. So can you so clearly this is a subring, because you choose 2f comma g inside c 0 1 r. What does it mean? This implies that f minus g is inside c 0 1 comma r, right? Because of this f and g are continuous, so their addition and subtraction is also continuous, and also this implies that f dot g is continuous, right? So this is very easy. So this is a subring of, okay. So okay, suppose you have a function f zero 1 to r, x goes to x, identity map. F is a function in c 0 1 comma r. This is continuous function, right? Identity map is continuous. So, and this is already contained in r0 1, right? Okay. So f is in c0 1. So is f is a zero divisor? In which ring? Is f a zero divisor? A zero divisor of c 0 1 r or r 0 1? In which ring, or whether both of the ring, in both of the ring this is a zero divisor or not, you have to verify. How do we verify? Let for zero divisor, let g be a non-zero function. Let g be a non-zero function. Suppose this is in c 0 1 to r, such that x dot gx, this should be going to 0 for every x inside 0 1, right? So this implies that x has to be 0. There is no other choice, because gx is non-zero function, x has to be 0. Or g of x should be 0, but g of x should be, I cannot take gx to be 0. So there is choice, choose gx 0 if x is non-zero, and any non-zero value, suppose some k is non-zero whenever x is 0. But is this function continuous? Is this function c 0 1 is inside c 0 1? No, this function is not going to be continuous, because whatever I have defined, just there does not exist, no, there does not exist, yeah, there does not exist function, continuous function, such that fx is non-zero at exactly one point. See here, there does not exist any function such that fx is not continuous function, such that fx, such that this is non-zero exactly one point. So here, this exactly one point, this is non-zero, so this function is not going to be continuous. So this is not a zero divisor, this cannot be a zero divisor in which case, suppose this, so in this case it is a contradiction. Gx is non-zero, you cannot choose here. Suppose you take g to be or r0 1, Okay, now you can think of this as a zero divisor. This is a zero divisor. X is, whether you choose x is 0, you choose x dot gx, this will give us 0, and g is a function in r01, just a function, but g is not in c01, right? Okay. Okay, so f is a zero divisor. This f is a zero divisor. Zero divisor in r01. Okay, but not in c01. Okay, so if it's a zero divisor in okay, in r01 but not in zero divisor, so it means that if it is a zero divisor in a bigger ring, it does not imply it is a zero divisor in the smaller ring, because c01 is a subring of r01, right? So since fx equals to x is a zero divisor in r01, so hence f cannot be an unit in r01. Unit, and if it is unit, if it is zero divisor, it cannot be an unit. We have proved in earlier lecture, right? So fx equals to x for all x inside 01 is a zero divisor in r01. Hence f cannot be a unit in r01. Okay, am I clear with you? Hence f cannot be an unit in r01. It cannot be an unit, right? So you can also prove this. How do you prove this? To proof is, I guess, easy. Let it possible. There exists g inside c 0, 1, r. Okay, f is not in unit. Suppose okay, there is no need to prove, I guess. There is no need to prove here. My question is, can it be an unit? Can f be a unit in c01? So f is not a unit in r01, so can it be unit in c01? Suppose there exists an g inside c01 such that f dot g is 1. Suppose this implies that fx dot gx, this is equals to 1. This implies that fx is x gx, this is gx, this is 1. So you have to choose gx to be 1 by x, but this only define only if x is non-zero. You define gx as a function 1 by x if x is non-zero, and any non-zero value, suppose some k which is non-zero if x is 0. But this is not continuous, but the g is not continuous. This implies it cannot be an unit also in c01. This not continuous, g does not inside c01. Okay, this implies that f is not a unit in c01. Okay, If cannot be unit, also here. So I guess I think I have to do one more example, or so I let's deal with two ring, which is r to the power r, that means set of all function from r to r, and cr, set of all continuous function from r to r. Okay, this is f r to r continuous, and this is f r to r just function, right? Check. I'm giving you exercise. Suppose f comma g is a function from r to r, and if fx equals to sin x and gx equals to e की power x, this out of these two, f and g, who are unit, who are zero divisor, who are unit, and who are zero divisor, and in which ring, and in which ring. This is the exercise. You check. Okay, you have two ring, this one is one ring, this one is one ring, so you have to check for who are them are zero divisor, who are them are unit, in which ring. That's all. Okay, so I think, let me see what I have to. Okay, I'm lifting out with something. Yes, so there are some more things here. These are the countings. So zero divisor, okay, that's been over. Okay, okay, I'm giving you some more exercises, and we'll discuss in the next lecture. I guess I have to discuss in the next lecture. These are some basic exercises. I just gave, let me give some 2 or 3 exercises. We just prove it. Okay, I will give some hint also. Let rs be 2 ring, there is no sub ring, there is no, just 2 different rings, right? You just prove, first you prove rs are commutative if and only if r cross s is commutative. Okay, very easy to prove. R and S ring with unity, if and only if R cross S is so. Okay, third you prove idempotence of R cross S. I guess this has been proved. IR cross IS. I guess you just take one element here, you just show this is also here, and that's it. And you just prove or disprove jet of r cross s, sorry, jet of r cross jet of s. Jet of s means 0 divisor. R Cartesian product is 0 divisor s is actually jet of r cross s or not. You have to show. This one is prove or disprove. This one, I guess there will be one inequality will hold, either this or this. So this is not, maybe this is not equal. Either you have to prove or you have to disprove. Okay, so I think this is enough for today, right? You just these are some exercises, you just compute them or you just go through them, you will get. And I'm from here I'm ending the ring theory, the basic part. From tomorrow, from the next lecture we'll define some characteristics. We'll define characteristic of a ring. After that we'll go to ideals. After that we'll go to homomorphisms. Okay, homomorphisms, yeah, that's it, homomorphism. And then we'll PID UFT. Okay, then we'll go to reducibility. Yeah, so I think this is for enough for today. Thank you.